All right, looking for question 6 are asking for under a bunch of different circumstances to graph a function that meets those conditions or explain why it can't exist. So the first thing we're asked for is a function that's continuous at a equals 2, but not differentiable at that point. So it is possible to have a function that has continuity, but not differentiability at a point. So what does it mean for a function to be continuous? Well, that means that the limit of the function exists at that point. So let's kind of handle these things one at a time. So x equals 2. So the limit exists there. So what does that mean for the limit to exist? Well, as I approach from the left, I have to be approaching something. And as I approach from the right, I have to be approaching something. So that's for the limit exists. But also the limit has to be equal to whatever the function is. So now we have continuity at that point, which I think we've handled. But now we also want to have, well, we want differentiability to fail to exist there. So how might that not happen? So if our function is not differentiable, that means the derivative cannot be calculated. The derivative does not exist. And the way that that's going to happen at a point where we have continuity is if the tangent line we draw there is not unique. So let's come at this again because I think the graph I drew is going to be both continuous and differentiable. So let's make it a little more obvious. As long as I have continuity, and this is one way to make that look, I would say I have continuity here because the limit exists. The function is defined at that point, and the limit agrees with that function definition. But there's no way I can draw a tangent line at that hard corner. So I think I have continuity, but a lack of differentiability. Again, when you're drawing a graph that meets these conditions, there's probably lots of ways to do it. Yours might not look like mine does. Part B, a function that is differentiable but does not have a limit at a equals 3. This is actually impossible. And let's talk about why it's impossible. If you have a function that's differentiable at a equals 3, then you were telling me this. G prime of 3 exists. Now, what does it mean for G prime of 3 to exist? That means this limit exists. G prime of 3 is equal to this. The limit as h approaches 0 of G of 3 plus h minus G of 3 all over h. This limit cannot exist if this limit doesn't exist. The limit as x approaches 3 of g of x. And if we're told that this limit doesn't exist, that means that we have no continuity at x equals 3. And one of the big relationships between continuity and differentiability is if you have differentiability, you have to have continuity. Differentiability at a point necessitates that we have continuity at that point. So since they're asking for a function that's differentiable, but the limit doesn't exist there, we can't even have continuity because one of the conditions of continuity is that the limit exists at that point. So this is actually impossible. Moving on to part C, a function that has a limit. So let's just kind of break this down into pieces. So the limit as x, or sorry, the limit as x approaches -2 of h of x exists. We're also told that h of -2 exists, but h is not continuous at x equals -2. So let's do this again. Let's break down the definition of continuity. And those conditions are very close to what we have here. So continuity at x equals, I'll just say -2. That's the exact point we're looking at. We have to have that h of -2 exists. We have that we agree there. We also have to have that the limit as x approaches -2 of h of x exists. We also have that. But in the definition of continuity, we have to have that those two things agree. H of -2 equals the limit as x approaches -2 of h of x. But that's the thing we cannot have. So that's where we differ. So basically, what we want to do is this. We want to meet this condition and this condition, but fail this one. So basically, we can have h of -2 existing. So let's draw a graph here. So h of -2 exists. Let's say it exists right there. We also want the limit to exist. Okay, let's say it exists here. So now the limit looks like it exists at x equals -2. The function looks like it's defined at x equals -2. But do we have continuity? No, because that limit and that function definition do not agree. So I think we've met the conditions there. And finally, part D, you want a function that satisfies all of these. So let's handle it one bullet at a time. We have that p of -1 equals 3. So let's do this. Let's be optimistic and assume that this can be done. And we'll just start doing it. So the limit, so p of -1 equals 3. So -1, 1, 2, 3. The limit as x approaches -1, the p of x is 2. So this is pretty similar to what we just did. So I think that right there satisfies the first bullet. So we'll mark that. P of 0 equals 1. Okay, so I'm a little too aggressive with my graph here. So let's throw this out. P of 0 equals 1 and P prime of 0 equals 0. So I think I can honor that point here. So P of 0 equals 1. We're also told that P prime of 0 equals 0. So what does P prime of 0 equals 0? What does that mean? Well, that means that x equals 0, we have to have an instantaneous rate of change of 0, which will look like a place where you can have a horizontal tangent line. So I think I can do this. Make sure I reach that point, but I also want to reach that point with a horizontal tangent line, and maybe I'll continue going up after that. So now I think I've handled the second bullet. So at p or at x equals 1, what do I want? Okay, I want the limit as x approaches 1 of p of x to be equal to p of 1. So what I'd like to point out here is this notation here. I'm going to say this exact same thing in a different way. P is continuous at x equals 1. Because this one little statement contains all the conditions of continuity. The limit exists at x equals 1. The function is defined at x equals 1. And finally, those two things agree. So I have to have continuity at x equals 1. But is that enough? That also says that p prime of 1 does not exist. So this, I'll say a different way. P prime of 1 does not exist. That means p is not differentiable at x equals 1. So I have continuity at that point, but not differentiability. The thing that I've been doing with my previous graphs has been having that hard corner. that shows that like I can't have a tangent line there. One thing that I haven't shown yet is another way for us to fail to have differentiability is maybe I have a vertical tangent line there. So maybe the slope gets so steep that it's essentially vertical before it settles out again. So that's another way for differentiability to fail to exist. Maybe the instantaneous rate of change is infinitely large, which means the derivative approaches infinity, which is another way, is a specific way of saying the limit fails to exist. So I believe this graph is possible to make, and we showed a good example of it.